Hey guys, to try something different this time, I'm going to actually use the projector for our review video, so hopefully it works out. Give me some feedback on Monday if it worked out or not. But I think it will. Before we get started on the review video, there's a couple things you should take note of. One, our test is Monday, review is also due Monday. Here's those probabilities I told you about on Friday for number 5. That will be helpful with number 5 because we did do number 1. I can't say this one is 8 out of 52. Also, here's some equations for calculating probabilities, especially when we don't have a table. Usually if they don't give us a table, we can assume the events are independent, meaning we can do this multiplication, okay? And then we can use multiplication for the OR statement. Now, if they do give us a table, then we can't use this one anymore because we don't know if they're independent or not. But we can still use this one. We just got to find our AND statements in the table. And we'll practice finding some AND statements in the table. Also, in order to show two events are independent, A and B are independent if probability of A equals the probability of A given B, and if the probability of A times B equals the probability of A and B. Now, usually they ask you to do this if they give you a table. So if they give you a table and I want you to tell me that events A and B are independent, then you have to show one or the other, okay? And you can get A and B from the table, A and B where A overlaps B. You can also find these in the table as well. And we'll go through some of that practice. So I'll leave that up there so you can copy down for a second while I go shut the lights off, and then we'll go from there. All right, hopefully what you see on the screen right now looks familiar. It is part of your review. Now this first question says, in the table below, list all possible rolled sums of 2 6-sided dice. Make a probability distribution for all sums of the outcomes. Now real quick, how many outcomes total are there going to be? Well, 6 is one dice, times 6 is the other dice, equals 36 total outcomes. And if you count the number of squares in my table, you get 36. Now if I'm going to start filling in this table or my sample space, what I'm going to do is I'm going to do, the left side is one dice, the top is their dice. So if I roll a 1 on one dice and a 1 on their dice, they get 1, 1. Okay, some of you like to write like the sum in there, like 2 right here. 1, 1 is fine. You can also write 2 there because 1 plus 1 is 2. That works well. The next one would be 2, 1 and 3, 1, and so on. And the next row would be 2, 1, 2, 2. 2, 3, and so on. The order doesn't really matter in this case. All right, so that's how we fill in our sample space. Over here in our probability distribution, we need to make a list of all of our possible sums and the probabilities of each. Now, in every sample space we look at, the lowest sum is usually top left corner. The biggest sum is usually bottom right. All right, and you can actually find all of your sums by going down the first row and across the down the first column and across the last row. All right, so if we had this filled in all the way, it'd be 4, 1, 5, 1, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So I can actually get all of my sums by going down this column and across that row. 1, 1 makes 2, 2, 1 makes 3, 3, 1 makes 4, 4, 1 makes 5, 5, 1 makes 6, 6 and 1 makes 7. 6 and 2 makes 8, 6 and 3 makes 9, 6 and 4 makes 10, 6 and 5 is 11, 6 and 6 is 12. Once again, those are sums, so I'm adding those. Now to find the probabilities, I need to look at my table and see how many times each one appears. Now I'm deliberately not filling that all the way in because I need to leave something for you guys to do. Well, a good way to find our probabilities is to find how many 2's are in the table. So I look at all of my outcomes, and I notice that 1, 1 is the only 2 that's in the table, the only sum of 2 that's in the table. So my probability is 1 over 36. Okay? Now, if you remember from the day we talked about these, there are the diagonals of the table. Those diagonals look like this, and actually everything on those diagonals have the same sum. So when you're trying to figure out how many of each sum there are, you can always draw these diagonals, and those diagonals will help you figure out each sum. This diagonal is 2, this diagonal is 3, this diagonal is 4, 5, and 6, and so on. think you guys can figure those out. All right, so that's how we can do problem 1. All right, once again, I did leave some for you to work on your own. Now for 2, it says suppose you are munching on some M&Ms that come in a brown bag, which you obviously cannot see into. You are trying to find the probability of choosing a specific color when reaching into the bag. Each time you do this, you put the M&M back into the bag. I guess we're not really munching on them, we're just kind of using them for math class now. Put them back into the bag and choose the next one. Your results are as follows. So, think about it as you dumped out all your M&Ms, you counted all your reds, your greens, your blues, your orange, yellows, and your browns. First thing you should do is find the total, because if you remember, probability is the amount of successful outcomes over the total. So we add all these numbers up, and we get 160. So our total number of M&Ms is 160. That's a big bag of M&Ms. All right. To find the probability of blue, yellow, blue or orange, pink, not yellow, we need to use that table. Now I'm going to do some that are similar to these ones, but not exactly the same. We're going to find the probability of red. Okay. So the probability of red, we take the total number of red, 24. And so that's our total number of red, and we divide by the total, 160. 24 over 160, that does reduce. It reduces down to, the way to do this is use your calculator, do 24 over 160, math, frac, enter, and you can get what it reduces to. I'm going to try to do it in my head real quick. So it's 12 over 80, which we reduce again to 6 over 40, which we reduce again to 3 over 20. Yeah, good job, Mr. Branch, 3 over 20. So the probability of red, all reduced down, is 3 over 20. All right. Now, if I want to find the probability of not red, which is going to come in handy later for you, find the probability of not red, we do 1 minus the probability of red. You could use either one because it's the same number. So 1 minus the probability of red, which is 1 minus 3 over 20, is 17 over 20, and that cannot reduce. If you use 24 over 160, when you do 1 minus, you'll get 136 over 160, which reduces to 17 over 20. Okay? Hopefully that makes sense. Now there's some sort in there. There's one like blue or orange. Okay, so in order to do blue or orange, that's the probability of getting blue or the probability of getting orange. Now if you remember the equation from the beginning, to do the probability of blue or orange, we got to do the probability of blue plus the probability of orange minus blue and orange. Okay, now I don't want to do one for you, so we're going to do green or yellow. Okay, so the probability of green is 26 out of 160. The probability of yellow is 22 out of 160. And then we got to subtract green and yellow. Now, can I draw an M&M that's both green and yellow? The answer is no. So we subtract a 0. So 26 over 160 plus 22 over 160. This ends up being 48 over 160. Becomes 24 out of 80. 12 out of 40. Take 4 out of each of these, so 3/10. All right, so green and yellow will reduce to 3/10. But all right, so hopefully that makes sense. Once again, total green 26, total yellow 22, minus 0 because there's no M&M that's both green and yellow. All right, let's move on to probability of drawing 3 in a row. So now we did blue. You guys have to do blue on your own. So I'm going to change it to red. All right, once again, I kind of want to still make your review a little tough on you. So I'm going to change that to red. So the probability of red, we did earlier, was 3 out of 20. So the probability of getting red 3 times in a row, that means the probability of red and red and red. So to find this, we do 3 over 20 times 3 over 20 times 3 over 20. Okay, 3 over 20 times 3 over 20 times 3 over 20 equals 90 over, or not 90, what am I talking about? Equals 27, because 3 times 3 is 9. 9 times 3 is 27. 27 over, thinking 800, I want to check just to make sure. Oh, 8,000. Man, Mr. Branch, nice job, you messed it up. Over 8,000. But your answer should be a little bit different because you're doing blue 3 times. Okay. Next one, what's the probability it takes That's probably it takes you exactly 4 tries to draw your first yellow. Now I'm going to switch that one to red as well. Now if it takes me exactly 4 draws to draw my first red, that means I'm trying to find the probability of not red, and not red, and not red. So that's my first 3 draws. And then the probability of red. So to get this, we take not red, which we found earlier was 17 over 20, times 17 over 20, times 17 over 20, times 3 over 20. So if I calculate that, then I'll get the probability of not red. Or sorry, probably takes 4 tries to draw your first red M&M. So once again, first draw, second draw, third draw, fourth draw. All right. What is your probability to draw 5 times and never get a red? Well, this one I'll stick with the red. I'll give you one for free, I guess. So it's probably draw 5 times and never get a red. Well, the probability of not red, once again, not red we found earlier was 17 out of 20. So if it takes me 5 draws and I never get a red, that means it's the probability of not red, not red, not red, not red, and not red. So I should be using 17 out of 25 times. So it'll be equal to 17 over 20 times 17 over 20 times 17 over 20 times 17 over 20. And that's 4, and there's my 5th. And since this time I never got a red, they're all the probabilities are the probability for not red. So hopefully those help you out. Right. Now if we go further down the page, for I and J, we can find some more probabilities. Now I and J are still, or I is still consecutive probabilities. So it's everything we've been doing before, but now I'm looking at it takes 3 or less to get an orange. Okay, so if it takes 3 or less to get an orange, if it takes 1 try, that means I got an orange on the first try. So 1 try is the probability of orange. That's what 1 try is. 2 tries is the probability of not orange, because I didn't get it on my first try, and then orange. Okay. Now if it takes 3 tries, that means it's the probability of not orange, and not orange, and then orange. Now since these are and statements, sorry, this one is just the probability of orange. It'll be 34 over 160. These ones, since they're and statements, that means you do the probability of not orange times the probability of orange. Okay? Not orange times not orange times orange. Now you're probably wondering, how do I get the probability of not orange? Well, if I know the probability of orange, I use my table from up above. It's 34 over 160. So that means the probability of not orange is 1 minus 34 over 160. So then, when I'm going through these, it'll be 1 minus 34 over 160 is 126 over 160. And those can reduce. You can reduce them if you want to. You'll get the same answers. But so for this one, it's just going to be 34 over 160. For this one, the second try, I got not orange first, so 126 over 160 times 34 over 160. And then 126 over 160 times 126 over 160 times 34 over 160. Right? Now, when you do that, you'll get something close. It's approximately 0.51. Okay, you'll get something close to there. Right? So when you try it out on your own, and please do this work all on your own. Okay, just watching me do this isn't going to help you. You need to be doing this review as well. All right, so that's the probability of 3 tries or less to draw an orange. Now, I think I might have gone over this a little too quickly. When you find these probabilities, this is the probability it takes you 1 try to draw an orange, 2 tries, and 3 tries. The probability for 3 tries or less, you need to take what you get for each of these and add them up. Because with OR statements, you add. 3 tries or less means it can be the 3rd try or the 2nd or the 1st. So you're going to add these probabilities up and you'll get 0.51. All right? Now to find the probability it takes 4 or more, you got to think about it this way. 3 or less and 4 or more, that encompasses all the possible outcomes for trying to get an orange M&M. All right? It could take you 1, it could take you 2, it could take you 3, 4, 5, 6, and so on. But all the possible outcomes are encompassed in these 2 statements, 3 tries or less or 4 or more. So these 2 probabilities should add to 1. So to find the probability of 4 or more, we do 1 minus the probability of 3 or less. Once again, that's because these 2 should add to 1. The probability of drawing an orange M&M over the whole span of that bag is going to be 1. So to find the probability of drawing 4 or more, or taking 4 or more to get an orange, we do 1 minus 3 or less. So hopefully that is helpful. All right. Now, you can see 3 down here. It says, if 40% of the U.S. population likes to show Big Bang Theory, I am one of those 40%. Make an area model that shows the probability that your teacher and your principal likes the Big Bang Theory. All right. Now, my hint to you here is write 40% as a fraction. Okay, 40% is 0.4, which then can be, if you do math frac, you do 0.4 math frac, you get 2/5. Okay, you can also think of 40% as 40 over 100, which also reduces to 2/5. So what this tells me is that for the area model, for me and for Mr. Friends, we each need 5 sections because it's 2/5. 2 of those sections are yes, we like it, and the other 2 are no, we don't. So yes, yes, yes. Oops, that's a no. No, no. Okay. So once again, 2 yeses, 3 nos, 2 yeses, 3 nos. Now the area, so that's our area model for me and Mr. Friends liking Big Bang Theory. Now it says shade the area that represents the probability that your teacher, me, likes Big Bang Theory and your principal does not. Well, I take my row, my yes row, and I see where it overlaps Mr. Friends' no column, and we get these 6 boxes. So the probability then would be 6 out of 25. So hopefully that helps you out. All right. For number 4, it says that 56% of the sophomores like hot Cheetos and 7% wear sandals. I know I used the wrong wear. Once again, I can't spell. You guys know that. Okay. 7% wear sandals. Use these percentages to calculate each probability of the sophomores below. Now, before we get started on this, does liking hot Cheetos affect your footwear? No. So these events are independent. Okay. Once again, 56%, if you want to work with fractions, is 56 over 100. Okay. 70% is 70 over 100. Okay. Probability of not wearing sandals. In order to find the not, we do 1 minus 70 over 100, which is 30 over 100, or 3 over 10. Probability of not liking hot Cheetos. We do 1 minus 56 over 100, which equals 44 over 100. Okay, which reduces to 11 over 25. Okay. So hopefully that makes sense. Now, probability of likes hot Cheetos and not wearing sandals. I'm going to change that to likes hot Cheetos and wears sandals. Okay. Now, since it's an and statement, we can use multiplication. All right. We know they're independent, so we can use that multiplication rule. All right. So in order to find the probability of like hot Cheetos and wears sandals, we take the probability of liking hot Cheetos, 56 over 100, and multiply the probability of wearing sandals, 70 over 100. And then when I get that, that'd be my probability of likes hot Cheetos and wears sandals. Now, if it's likes hot Cheetos or wears sandals, once again, we're taking the not out, so that way you guys have one to try on your own. We'll do probability of hot Cheetos plus the probability of wearing sandals minus the probability of hot Cheetos and sandals. So what we did up here. So we can calculate that, and it'll give us the or statement. Okay. So once again, A and B are exactly what you need to do. C and D, I changed them. I took the not statements out. That's why I use 56 and 70 rather than the other numbers. All right. Now for E, it says that there are 156 sophomores. How many like hot Cheetos? Okay. How many wore sandals today? All right. So in order to figure this out, we have 156 total. 56. What we got to figure out 56% of 156. Anytime you got to figure out a percentage of the whole, we do 156 times our percent as a decimal. 56% is 0.56, or we can do 56 or 156 times 56 over 100. Okay, that works in any situation. All right. So 156 times 56 over 100, that gives us approximately 87. that means 87 of the sophomores like hot Cheetos. Okay. Only sandals today for you to do on your own. Okay, now the last one, or not the last one, the next one, number 5, all right, that's where you need to copy down those probabilities that I wrote down earlier for you to use. All right, I showed them at the beginning of this video. So if you don't have those written down, maybe you want to pause, go back, write those down so we can work with those. Now these are all and statements. You get your probability from the first page for orange and the probability for a club. Now since they're all and statements and we know drawing M&Ms out of a bag and picking cards out of a deck, those do not affect each other, they are independent. So that means I can use the multiplication rule. So orange from the previous page was 34 out of 160. A club, there's 13 clubs in a deck of 52 cards, it's 13 out of 52. So to find the probability of orange and club, we do 34 over 160 times 13 over 52. And then get our answer from there. Can try the next one. Blue and an ace. Probability of a blue M&M from earlier was 30 out of 160. The probability of an ace is 4 out of 52. So we multiply those together and we can get our outcome. Now I'm deliberately leaving those the way they are so that way you got some work to do on your own. All right, and the same thing works for the rest of these. All right, so hopefully that helps you out. All right, for 6. For 6, well, his students worked on a test. Mr. Branch collected the database. Okay, we've done the problem like this before. First thing I'll do is total them up. Okay, total people wearing sneakers is 25. Total not wearing sneakers is 9. Total of boys is 13. Total of girls is 21. And our grand total, just add up either the column or the row and use that one to check. So 13 plus 21 is 34. And check myself, 25 plus 9 is also 34. All right. Now I'm going to switch this around on us. We're going to first calculate the probability of girl and sneakers. Okay, I'm going to calculate the probability of girl and sneakers. So girl and sneakers is where girl and sneakers overlap. So here's my sneakers row, here's my girl column. It is this number 15. So that'd be 15 over 34. Now whenever I do and or statements, it's always over the grand total. Okay. Now for the next one, for an or statement, we're going to do probability of boy or not wearing sneakers. Okay. So to do this one, we look at the total number of boys. We do the total number of boys, 25 out of 34. And then we do the total number of not wearing sneakers, 9 out of 34. And we subtract the overlap, we subtract the and. So boys and not wearing sneakers is right here. So we subtract 3 over 34. 25 plus 9 is 34. Oh, I did it backwards. This is the probability of wearing sneakers. Probability of boy is right here, 13. Sorry about that. So probability of boy is 13 over 30. Probability of not wearing sneakers is 9 over 34. So boy is right here. Yeah. I think you guys see my mistake. So 13 plus 9 makes 22. 22 minus 3 is 19. So this probability right here is 19 over 34. All right, now use the same ideas for A and B. Now for C, once again, I'm going to throw a little kink in the plans. Instead of doing wearing sneakers given girl, we're going to do wearing sneakers given boy. Okay. So whenever you have a problem like this, you first look at all of the boy. Okay, so we're going to look at this row first. Okay, what's the total in that row? Playing along at home, you know it's 13. Okay. And then we look just in this row at how many people are wearing sneakers. That's 10. So the probability of wearing sneakers given boy is 10 over 13. Okay. Now remember, if events are mutually exclusive, meaning they both can't happen, then the given statement is 0. Okay, look further on. If I did one where it's probably wearing sneakers given not wearing sneakers, you can't be wearing sneakers and not wearing sneakers at the same time. So that'd be 0 because those are mutually exclusive. Okay. Now, if you go further down on the next page, it asks about independence. Okay, so let's wonder if wearing sneakers and boy are independent. Now, if we remember, two events are independent if A given B equals the probability of A. So if this is the case, two events are independent. Right? So here we have wearing sneakers given boy, so we need to compare that to just wearing sneakers. Okay? Since wearing sneakers is in the A location. All right? If you compare it to wearing to boy, that's not going to help us. So we got to compare it to wearing sneakers. So wearing sneakers is 25 over 34. Okay? Now looking at those fractions, we can probably see that they're not equal. So we can check to be sure. 10 divided by 13 and 25 divided by 34. Okay. So 10 divided by 13. So this one is point. Well, you probably can't see that. Okay. So this one is 0.76, and this one is 0.74. Okay. I would make an argument that those are close enough to be considered independent. So my answer would be yes, they are independent because these are close enough. However, since they are not exact, you could also make the case that they are not exact, so they're not dependent. But that is up to you. Okay. Last question I asked you in this section for number 6 is, what are some mutually exclusive events? Remember, mutually exclusive means they cannot happen at the same time. For example, wearing sneakers and not wearing sneakers. They can't happen at the same time. Okay? Those be mutually exclusive. Also being mutually exclusive, being in Mr. Branch's class and Mr. Plain's class. Can't happen. Okay? Being at school, being at home, mutually exclusive, you can't do them at the same time. Right? I guess this kind of works. But so that's how we do number 6. All right. The last one is a model. You got to make a simulation model. Now I know that the simulation model, that came through awesome. All right. I know the simulation model stuff is probably the toughest stuff, so I would encourage you to watch my simulation model videos. There's 2 parts. They're linked on my Facebook page, where this will be linked, and they're also on my YouTube channel, where this will be put in as well. All right, but just keep in mind, they're talking about the World Series here. So the most number of games, so the most is 4. Oh, wow, that's wrong. The most is 7. They play best of 7. And the least is 4. So what you need to do in this case is you need to keep track of the number of people, or the number of games. Got to count the number of games until one team gets 4 wins. All right? So that is all for this review. This is probably my last video I'm making this year. So hopefully you've enjoyed my videos, and good luck on your exam.